we are set to go. Venimos a Moisés, aquí está. A ver, vamos a esperar unos minutos. A ver si se puede volver a conectar. Moisés. Vamos a esperar unos minutos a ver. A ver, ¿dónde quedó Moisés? Ya nos regresó. A ver, ahí viene. ¿Ya, Moisés? Bueno, está conectado, pero no tenemos noticias de él. A ver por el chat, ¿qué dice? Ah, ok, entonces está teniendo problemas Moisés, muy bien. Bueno, a ver. Al inicio, cuando te conectaste la primera vez, Moisés, sí tenías al menos el video. No sé si tenías buena señal, pero al inicio sí tenías el video. Okay, so let's start then. So as I mentioned yesterday, today we will look at a new example of a manifold, which is the complex, the real projective space. So now we can see you, Moises. I don't know if you can hear us. Moises? Well, so we can see you now, your video. Okay, so in order to define the smooth structure of the real projective space and even to define the real projective space, I'm going to review a few concepts of point set topology and mainly the quotient topology. That's what we will need. So Moises is saying no, so I think he cannot hear us. Well, so let's review this. Again, this is going to be only topology, and then we will move on to the smooth structure. So we have a topological space. X, and on that topological space, we will define an equivalence relation. And you know that every time that you have an equivalence relation, you have the set of equivalence classes. So I will use X tilde to denote the set of equivalence classes. So I have a point, and this is the set of equivalence classes, and I will use this notation to denote that class, all of the elements that are equivalent to X. Right? And the whole idea is that here you have a topology, but there is no topology on this side. So the whole idea of the quotient topology is to make this space into a topological space. And it is a very straightforward approach. So a subset here is going to be called open or set to be open if the preimage under pi is an open set. So that's how the quotient topology is defined. A subset here is open if the preimage is an open set here. So this is what you cover on your topology class. And such definition gives you a topology on this space. And I will also denote this space like the quotient space. So every time that you have a topological space and equivalence relation on the set of equivalence classes, you have an induced topology, and it is called the quotient topology. And basically, the idea to define a topology here is in a way to make this map a continuous map. Right? Because recall that the definition of a continuous map, for every open set here, the preimage has to be open. And in fact, that's a characterization of the quotient topology. It's the topology on this set that makes this map continuous. Okay, now, so sorry, I said it wrong. The quotient topology is the largest topology such that this map is continuous, right? Because in here, you can always define a very trivial topology, the one that has only two sets, the empty and the total space. So that would be a topology here. And in that topology, this map is going to be continuous. The preimage of the open set is the open set, and the preimage of the total space will be X. So that topology will also make this map continuous. So the quotient topology is the largest topology that makes this map continuous. So that's the other characterization of the quotient topology. Right, so this is just a review of the quotient topology. Now, we can also start the other way. X is no longer a topological space, but X is a manifold. And then what conditions can we impose to make this into a manifold? So that's also something that it is very well understood. I'm not going to cover that right now, but that's also something that it is well known. If you have this quotient and this is a manifold, what are the requirements that you need to make this into a smooth manifold? But I will not focus on that right now. So we're going to define the real projective space first as a topological space, and then we will look into charts and put a smooth structure on the real projective space. So I'm going to consider Rn plus 1, and the idea is to think of that space as a vector space. So it is an n plus 1 vector space over the reals. So right now, I'm not going to consider Rn plus 1 as a manifold or even as a topological space. I'm interested in the vector space structure of this. So I'm going to remove the zero vector, and then this is going to be the space where we are going to define an equivalence relation. So I will take two non-zero vectors and say that they are related if one is the scalar multiple of the other. Okay, so that's my definition of an equivalence of a relation only on this space. So here I want to emphasize that so this definition is this, and I'm using concepts of vector spaces. So here you can consider any other vector space over any other field, and this makes sense. Okay? Right, so, okay. I'm not going to prove it, but this is an equivalence relation on the set. Okay? So we have an equivalence relation on this set, and let's think about this in a more geometric way. You see, this is saying that X and Y are in the same line or in the same linear subspace because one is the multiple of the other, right? Now, so in geometric ways, basically what we have here are one-dimensional linear subspace. So they all go through the origin. I have here X, and I want to know all of the vectors that are related to X. So I have to multiply lambda times X. And all of these vectors will be related to this one. Note that here the scalar has to be non-zero. Because if lambda is 0, I will get the 0 vector. But remember that the total space is the Euclidean space or the vector space minus the 0 vector. So I don't have that scalar. If I here have another vector, then all of them are related to them. And it is just a one-dimensional space minus the 0 vector. So in a geometric way, so a line or a one-dimensional subspace through the origin is the equivalence class. I just remove the 0 vector. So lines or one-dimensional subspace are the equivalence classes. Now, but you know very well that when you have an equivalence relation, the set of equivalence classes are disjoint. Two equivalence classes either agree or are disjoint. And that's the reason that we are omitting the 0 vector, because any linear subspace contains the 0 vector. So in that way, that's how we can understand this relation, right? And also, I'm putting a one-dimensional subspace. For instance, if you have a vector space over the complex, and you take a non-zero vector, the set of vectors that are related to it, or the equivalence class, is going to be a one-dimensional subspace over the complex. So over the reals, it is a two-dimensional subspace. But we need to keep in mind the field. So over the complex, a one-dimensional subspace, it has 2 dimensions over the reals. So keep that in mind. Okay, so this is the example that I want to stress. So you can prove this. We have an equivalence relation and we have the equivalence classes. The set of equivalence classes is what we denote by the real projective space. So right now, we have only the set, right? The set of equivalence classes is what we denote the n-dimensional real projective space. And now, what we covered at the beginning, now you can think of Euclidean space with the standard topology. And here we have a topological space. the real projective space has a topology induced by Euclidean space. One way of thinking of the real projective space is the set of one-dimensional subspace in Rn plus 1. Right? Because a class is represented by any point. Only one will give you an element here. So you can think of Rn as the set of one-dimensional subspace in Rn plus 1. Similarly, if we started with Cn plus 1 as a vector space over the complex, Cpn will be the set of one-dimensional subspace over the complex in Cn plus 1. Right? So now the whole idea is to understand a little bit this space and also to define a smooth structure on it. Okay, now remember that we have the projection map. So I have a vector, a non-zero vector, and I will map it to the equivalence class. Also, you can think of this as the one-dimensional subspace, the unique one-dimensional subspace induced by this vector. Now, something in this particular example, we're going to use a coordinate notation. So I have a vector, and I will use this notation to denote the class. Square brackets of there, okay? So let's try to understand this, right? So we have a notation for the points here. N plus 1 entries. First of all, notice, so these are real numbers. And notice that some of them could be 0, but not all of them, because we have this. Okay? So x naught can be 0, but not all of them can be 0 simultaneously. And also, the same point has different representative. For some scalar, which is non-zero, those represent the same point. Or also, if you have this, if I have 2 points representing the same class, that means this is the definition. Scalar multiplication of this vector. again from some non-zero scalar. So any point on real projective space has different representatives, but they are all related by a scalar multiplication. Okay? So now let's try to understand this in dimension 1. Right? So I'm going to study, I want to have a feeling what is RP1. The definition says you have to go to R2, remove the origin. So the zero vector is not included. And then what we know, I take any linear subspace. Let me draw a couple of them. Right? So if here I have a vector, non-zero vector, all of this line, removing the zero vector, is the class. Right? So it is, these represent 1 point on RP1. The same, all of these points together with these ones represent a single point in RP1. So RP1 is the set of all equivalence classes. So note the following. Let's do this. I'm going to draw a semicircle like this. Right? For the moment, assume that I don't have the two endpoints. I do not include the two endpoints. So note that any line intersects the blue semicircle exactly at 1 point. Right? So this class is represented by this point. This class is represented by this point. I don't have to go below the x-axis because this is the same as this one, right? So that's why I only draw the upper circle. Now let's look at the x-axis. So far, the x-axis, this is also one element in RP1. So far, it's not included in the blue curve. So I have to include it. So I can either include it on the left or the right. It doesn't matter. So here is open. So that half open curve is a bijection with all of the points in RP1. Everyone agrees? There's a one-to-one correspondence between lines that go through the origins and points in that half circle when one end is missing and the other one is not missing. Okay, now let's think a little bit about topology in a very naive sense. So let's focus on that point. And let's move the line. It's a continuous motion so that it will become horizontal. So this point will be this one and then this one. When it is completely horizontal, the point will lie here, right? And then you keep moving. In other words, RP1 is this. It's a circle. So I have to join the two endpoints of the blue half circle because they will represent the same line in RP1. And in that way, I have a bijection between the circle and the set of all one-dimensional subspace in R2. And it is not only a one-to-one correspondence, even in a continuous manner. So even the topology will be the same. So this is the upshot that I wanted to stress, that RP1, it is just the circle. Is that clear?
So we have to like stretch the semicircle that we have, right?
Right. So I mean, either stretch or lift it from the plane and join the endpoints. Yeah, so let's see. In a naive way, so you have this, and then you cut it, let's say like this, and then you will stretch it to get this. But something that it is very, very important here in the circle, in a continuous way, if you are walking like this, you are doing this. So here, when you reach here and you continue walking, you must go this way. And you can see that on this line, right? So first, you are here, and then you are here, you are here, and when you go below, you are here. Exactly if you're walking along the circle. So the continuous motion of the line goes within the circle. Any other questions? Now, as itself, RPN is a topological space, and only in this case, it agrees with something that you already know. In higher dimensions, there's no other example that it would coincide. But in dimension 1 is an example that you already know, and that's what you have there. Let's see. Let me give you the other example. So in R3, and we have to consider the lines in R3, okay? So I mean, you can look to a corner in your room and you have one quadrant of R3. So I have to remove the origin, okay? And then I must consider one-dimensional subspace in R3. So one example of this could very well be the x-axis, the y-axis, and the z-axis. Those are 3 examples of one-dimensional subspace in R3. Right? So now consider that you have the ball centered at the origin. So here, and you have the ball. So this is a 2-dimensional sphere. I don't know how to draw it very well, but you have it here, right? Now, let's look above the z-axis. So basically, all of the one-dimensional subspace, I have it on the top. I'm only missing the ones on the XY plane, right? Think of any line through the origin. that line is either in the XY plane or some part of it is above the XY plane, right? So you have only two options for a line. It's either in the XY plane or it intersects this set. Right? So basically on the northern hemisphere of the ball, we have all of the lines, all of them. So this line, maybe it intersects here and there. But if I look only on the northern hemisphere, I have basically a one-to-one correspondence with every line, every one-dimensional space, and the sphere. The only thing that I'm missing is what is happening on the XY plane. So for that, I need to consider now the lines in the XY plane. But what happens with a line in the XY plane? It's going to intersect let's say this line here. Is exactly the picture that we have here, right? This R2 is exactly the same as the XY plane. So in order to have a one-to-one correspondence, you take all of the northern hemisphere with C positive, and with C0, you only have to do this. What do you take in this case? You at this point, you move through the equator and omit this point. So once you do that, you will have, well, I'm sorry, basically, the way to do it is this. Consider the whole hemisphere. I'm sorry, the whole equator. And remember, the equator, 2 points in the equator represents only one line. So in order to get RP2, and this is the most common way that you will see it, think of the northern hemisphere as the disk. So put it flat, only the northern hemisphere. So this line is the equator of the sphere. So this point and this one are the same. This point and this one is the same. and so on. When you put them together, you will get RP2, which again, that's not a very nice picture. You cannot see it very well in three-dimensional space, because when you put this and this together, you get a taco, right? So you just fold it and you join those 2 points. But then you have to move around that one to that one. So if you do it on tree space, it will have self-intersections. So let me just I want to, let me look for a picture if you want. Okay, here we have it now. So you see, that will be an example. So it is hard to construct, to imagine. Let me find another one. Yeah, so this one here, when you see the pointer doesn't show, right? You see the ball, and then blue and red. You have to make the identification with opposite points on the equator. Do you see this picture? The one on the right. You just see the ball, and on the top a circle, half red, half blue. If you make the correct identification, you will get RP2. And in fact, there it is also, right? But it is something that you cannot visualize in R3 because it will have self-intersection if you do that. Okay, are there any questions for this?
No.
So I'm just trying to make you have a feeling of what is the RPA. RP1 and RP2. Okay, now so let's get back. So we want to understand RPN. Remember, that's the notation that I'm using for the points, square brackets. And I'm going to consider a very specific subsets. So U naught is the set of all points in projective space such that the first entry is non-zero. That's the only condition. So notice that under this hypothesis, this point is the same as 1, because x0 is non-zero, so I can divide by it. So it is the set of all points such that the first entry is 1, and the rest could be any number. Know that all of this can be 0. That's allowed, because here this is non-zero. Okay, so I'm going to consider those sets. U0, U1 is defined exactly in the same way. Points in projective space. Now x1 is non-zero. And so on until n. I have un. So I have n plus 1 sets, subsets, or RPN. Now the intersection is non-empty, and that means that all of the entries must be non-zero. Okay? So that is a big set. But now I would like to understand the pre-image of all of them. So for U0, I have all of the points here such that this is non-zero, the first entry. Right? Do you agree that that's an open set in Euclidean space? Yeah, I mean, the complement of this, what is it?
The complement is a hypersurface, right?
Exactly. And it is closed.
Yeah.
So that's why this is open. And remember that we define RPN as a quotient of an equivalence relation. So RPN has the quotient topology. And this set is an open set in RPN. And in fact, all of them. So I have n plus 1 open sets in RPN. And I'm going to use these open sets to give Rn a smooth structure. So basically, these n plus 1 sets are going to define an atlas on RPN. So far, they are open. Moreover, the union of them is RPN. So I have an open cover of the projective space. All that I need is a homeomorphism defined on each one of them. And that is going to be not so complicated. So I'm going to define the map. And in fact, this map is going to be onto. The image is going to be all of Rn. And also, that's the reason that we have the index here, right? This is the dimension. That's why we have here one dimension higher. So this n is the dimension once that we show that it is a manifold. So, okay, this is the map. Recall that x naught is non-zero. That's why it's possible to divide by it. So this makes sense, right? So that's the map. The inverse is this one. Now, you can check that both of them are continuous. Remember that here we have a topology. So in that way, we have charts and they're going to be compatible. I'm not doing the computation that what happens on the intersection, but you can work it out. But we have an atlas by those charts. And remember, this map is defined here, and the image is all of Rn. So the homework is to check that they are compatible. Okay, so you can see that they are compatible. So you have an atlas on RPN. And this map that I defined here are very important because they are like basically canonical maps. So for j between 0 and n, xj is non-zero, x1 over xj, that's the map, and that's going to be a homeomorphism, and all of them will give you an atlas. Questions? So let's look in this into more detail for n equals to 1, right? In this case, we only have two open sets. Here are the maps. And I want to understand this a little bit more. So no, let's start here. Let's see. RP1 x naught x1 right? X1, x2 could be any real numbers, except they cannot be zero simultaneously, right? Now, U naught, sorry, x0 is non-zero. Right? Now, x1 over x0 could be any real number. So basically this is now what I want you to tell me is, what is this? What is the complement of U naught?
Like a subset of RP1 where x0 is 0.
And what is that?
U1.
No, 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 no.
No, no,
Wait.
no es cierto. No es cierto.
Now,
It's like an axis, right?
but now here, because the first entry is 0, I need to make sure that x is non-zero, right? Because I cannot have all of the entries to be equal to 0. That's not allowed. Some of the entries can be 0, but not all of them at the same time. Now, x is non-zero, so I can divide by x. So the complement is only 1 point. And similarly for the complement of U1. Is this clear for everyone? Okay. So basically, U0 is the whole manifold except 1 point. U1, the same, is the whole manifold except 1 point. Now, remember what RP1 is? What is RP1? Remember that we studied the case n equals 1.
The circle?
Pardon?
The circle?
Right, S1. So what I'm saying is U0 is everything minus a point. So basically, these two charts are the same that we have seen before. The ones that you obtain by stereographic projection. So I don't know, maybe this is 0, 1. And this is 1, 0. So it agrees with this old example that we already covered here in class for the circle with two charts. Okay. So let's move on now. Right, so the punchline of all of this is what we have here. RPN is a smooth manifold of dimension n. Good. Now, so remember the whole idea of this. I mean, before this class, you already have the notion of Euclidean space, open subsets of Euclidean space, and you can talk about smooth functions. You can take derivatives. And one of the motivation of this is that we have other class of objects that generalize Rn and the open sets, and they are the manifolds. And on these new objects, we can do the same things that you do in calculus in terms of derivatives. So I'm going to consider this function. I look at that function on Euclidean on RPN. It is defined this way. But remember, RPN or this notation, I can have different representatives of the same class. So in order to talk about a function, I must verify that this is well defined. Because this definition is in terms of the x vector, right? But you know that any other representative is going to be a multiple, like this. And if you plug it in here, you can factor a lambda square on the top and also on the bottom. And so this function is well defined. Okay, now so you have this function. You can check that it is continuous, but you can do even more using the atlas that we defined before, you can show that this is a smooth function. Remember what you have to do for a smooth function. I'm just going to check that it is smooth on U0. Here we define the map on this chart. We even know what is the inverse. So in order to show that this is smooth, the definition tells us we need to check that this function is smooth. But what is that function? Remember that the inverse is this. And then if I apply f, I get this. And the only problem can come when you have a 0 here. But that is not going to happen, right? So this function is smooth. Because the only problem will be on the denominator, but it is never equal to 0, the denominator. Hence, this function defined on Rn is a smooth function. So this function on the manifold is smooth. Now, it is very interesting this, because more or less it justifies why do I take this function. Because note, if I don't put a square here, if it's just x1 plus x2 blah blah blah, then I can get a 0. And I will have a singularity, and the function is not going to be smooth. But because I have squares, I can guarantee that the thing at the bottom never vanishes, and so the function is smooth. So that's why I need to have this. And now, because I want the function to be well defined, if I have a square on the bottom, on the denominator, I will have a lambda square if I take another representative. And that's why I need to have also squares on the top. In that way, this is smooth, and that is why I took that function. That's why the denominator is x0 squared plus x1 squared, and so on. The constants a, those are irrelevant. They could be 1, 0, whatever, but they are irrelevant. Sorry, they are irrelevant to show that the function is smooth. Now, I'm going to make the constants more relevant to you. And let's assume that all of the constants are distinct pairwise. So you have this function under this condition, and what I want you to compute are the critical points of that function. Yesterday, we define the critical point, so a smooth function. So now the homework consists of find the critical points of that function, taking into account this restriction on the constants. Okay? Nice. So, do you have any questions up to this point?
No.
Good. Now, again, I'm going to give some other examples. I just want to take advantage that we started the class with reviewing the quotient topology. And there are other examples. I'm not going to say manifold, but let's say just topological examples that you can construct under this quotient. Oh, wait, I forgot something. No. So forget about the quotient topology right now. I'm going to make further examples of RP1. So RP1 is the set of one-dimensional subspace in Rn plus 1. There is nothing particular about being one-dimensional. So that's why, let's say that you are in Rn, vector space of dimension n, Rn, and fix a k between 0 and k. So you can also talk about the collection of all linear subspace such that the dimension of V is exactly k. Right? So in this new language, RPN is the collection of one-dimensional subspace in Rn plus 1. So for instance, what is this?
Like Rn.
So, right, so it's only one object, the total space. So this is only Rn, and let's say it's only 1 point. I know I put 1 here, but the other one is n0. What is that?
Why only 1 point?
I mean, because here,
Yep, there.
right? Because so this is the set of all n-dimensional subspace in Rn, right? And as you said, this is exactly right. So there's only one n-dimensional subspace there. So there's only one point. In terms of offsets, GLNN is only 1 point. Sometimes it's very convenient. We only denote the set of one element. We just put like this. Obviously, this can mean different things. In this case, means Rn, but it is only one object. So, okay, Jesus, is that clear?
Yep.
Okay, so now we go with Moises' answer. So now we're looking at this space. But Moises, so this is the set of all zero-dimensional subspace in Rn. So what is that, Moises? Why do you say Rn? Se cortó tu audio, nada más al principio se escuchó una palabra, Moisés.
Yeah. Wouldn't it be because it will be all the points in Rn?
Right. No, but yes, that's true. But of all of the points in Rn, you need to take a subspace. Like 1, 0, 0, 0, 0, that's a point in Rn. Is that a subspace? That single
The zero,
point?
maybe.
Jesus?
The zero.
Right. So there's only one. Only the trivial vector space that has the zero vector. Now that we are into this, so you are on the good track. Because I mean, this, it wasn't it was just, it has a more deep meaning. Why do we get zero? Well, a point and a point. It's because you can have a bijection here. In Rn, consider the standard inner product or any other linear product, inner product on Rn. And then note if you have a linear subspace of dimension k, the orthogonal complement is also a subspace and is of dimension n minus k. So at the level of sets, you have this bijection. If you have a k-dimensional subspace, you have a unique complement that has dimension n minus k. And using the fact that you have an inner product, that will give you a bijection between nk and n comma n minus k. And that's what happened here. If you have Rn, the orthogonal complement is just the zero vector. So that's a relation between these sets. And so in general, remember that this is a generalization of the projective space. These spaces are called Grassmannian manifolds. So we are not going to go further into details, but they have a smooth structure and they become manifolds. And in fact, this will happen to be a diffeomorphism between the two manifolds. Okay, very good. So now this is what I'm going to consider what I said before about the quotient topology. I want to give you some other examples about this quotient relation because it gives you very nice examples. In one way or another, you have seen this before, but not in this context. So take X, your topological space, to be the reals. And you put a relation there. Two elements are related if the difference is an integer. Do you know what is the quotient space?
Like the integers module their residue.
No, it will be R mod C, but what is this? So this is the notation that you use, and it is the circle. This is other notation. Right? So if you have this point, let's see what is the equivalence class of that point. All of the other real points that are related to that, you just add or subtract an integer. So here, you go here, here. That's one class. If you're here, the same. Right? So we have the same picture, well, kind of, like this. And you have to join those 2 points and you get the circle. Moreover, I mean, pi, you even know an expression for pi. When you consider S1 inside the complex numbers. So T maps to this number. When T equals 0, you are here. On 1, when T equals 0, the 1 complex number or 1, 0 in R2, and the preimage is exactly all of the integers. If we're moving up, then I have purple. Purple, I don't know, is somewhere here. And then I put the yellow one. I think here is the yellow. And then I put the red one somewhere here. So this is the map. Under this. So that's an equivalence relation on a set which is R, and the quotient space is the circle, and that will be the topology. And I decided to start with this example because this example has a generalization like this. Right? So the difference between the first entry must be an integer, and the difference between the second entries must also be an integer. This is an equivalence relation on R2.
Does it have to be the same integer?
No,
Oh.
no. That's why it's a comma, they don't have to be the same. So in that way, let's put a point and all of the points related to that red dot are precisely, well, hold on. This is the integral points. You have the origin, 1, minus 1, minus 2, 1, 2, minus 1. So let's start with the blue point, which is 0, 0. All of the elements that are related to 0, 0 are precisely all of the points with integer entries. Now, all of the points related to the red dot will be something like this. Okay? And so on. What you get here is something that it is called the torus. And remember that we have seen this. Which is related to the first example. This might correspond to this, let's say. And when the two intersect is the origin. So this is a way to give a topology to the torus, right? Now, maybe here is important to what we discussed here, how the points were close to each other. And also when I was trying to make sense of RP1, that the points are close to each other. Okay. So let's do this, right? I take an open set here. This is something like this when I go down. But when I take the pre-image, I will get all of those disks. So I will get this one and so on. Okay? That's the pre-image of that disk on the torus. And all of them are supposed to look the same. Any questions?
No, no,
Have you seen this example before?
not me.
No?
No.
Okay. Yeah, I mean, these kind of examples are very important because it will build intuition. Like, let me make a few comments here. You see, one way or another, you have studied a few problems regarding smooth functions on the circle. So you have been studying smooth functions on the circle, studying as a manifold, because you have seen functions here, there are periodic. Periodic functions on the real line is the same as functions on the circle. So any problem in the past of a function, of a periodic function defined on the real line, it was a problem of a function defined on the circle. Definitely, you only knew how to take derivatives in the real line because you didn't know that S1 was a manifold. So in order to avoid going into manifolds and showing that the circle is a manifold, you just consider periodic functions of the real line. And that's good. But not all manifolds are like that. So also, if you study functions on the plane which are periodic in the x entry and the y entry, you were studying functions on the two-dimensional torus. Also, this is something very important because you know this. I would do it here. Look, instead of taking all of R2, I'm going to take the square. So this is my topological space. 0, 1 cross 0, 1. Okay? I'm going to show you another way of getting the torus. So I'm going to define an equivalence relation on X. Let's say let me see. How do I write it down? I'm having trouble. No, this is wrong. X prime. Okay, so this is my definition of when 2 points are related. If the x entry or the y entry is not 0 or 1, there's no relation. This point is related with itself. Okay, remember that here I have 0, 1, 1. Right? Because this is my space. So if my point doesn't have a 0 or a 1, it is related only with itself. There is no relation. However, what happens if a point has a 0? Here, if x is 0, then y could be anything. Oh, sorry, I forgot to put y prime also. Okay, now. So if x is 0, it's going to be related only to those points where x prime has to be 1 and the y's are equal. Sorry. That's the right answer now. Now I know it. Right? So these two are related. x0, x prime is 1, and the y's are the same. Another one, here, the x is 0. I'm sorry, the y is 0. I'm on the other side. Why don't you tell me that I'm making it the other way around? X is 0. X is 0, x prime is 1, and these are related. Another one, x0, and then xy. And then the other one, x has to be 1, and these two are related. The other case when they can be related is when y is 0 or 1. And this is what I was drawing at the beginning. When y is 0, you are here, and that will be related with the same x to y in 1. Another one, y is 0 here. The x remains the same, and now y equals to 1 here. And remember that the points inside the square are only related to themselves. In this case, you don't have any, this is an equivalence relation, and what you get is the torus. Like that. it is exactly the same as before. It is given as an equivalence relation. And now let me just give you an example that this is something that you already knew before. So just focus on the square. And I'm going to draw here an apple. And maybe you played this game a long time ago in a cell phone. There's a snake that moves and eats the apple. But remember when you approach this wall, when you enter here, you come on the other side. And that's given by this relation here. And also, when you go down and hit this wall, you came out on this side. And that's because you are relating that point. So this is 0, some y, and it is related to this 1, y. So that snake is actually moving on the torus. So you were playing that game on the two-dimensional torus with those identifications. Sometimes this is just briefly expressed like this. So you have the square. In order to avoid that notation that I wrote, they would write something like this. This side A is identified with this side in this direction. This side B is identified with this side in that direction. So that picture has all the information above about the equivalence relation that I expressed here. Okay, now my time is up. What I had here is, it is exactly the same, so let me just finish. If you would like to have the real projective space, think of this, half of the circle. And then if you glue like this, you will get the projective space. Because this point here goes here. This one, the opposites. It's not a circle anymore when we identify points on the boundary of the circle. It's a square, but you get the same. And let's see, just to finish the last drawing. Well, so this is and here let me give you the clay model. You do exactly just glue these two. So you obtain a cylinder, and you identify the other ones, the opposite sides, but in opposite direction. So that equivalence relation, when you look at the set of classes, you get the claim model. And the other one, the projective space, and the other one was the torus. So the time is up. I don't know if you have any questions.
The square in D is the projective space for which dimension?
Oh, right, yes. Yeah, so this is a dimension 2. Because remember that in the interior of the square, there's no identification. Each point is their own class. Only on the boundary, we are making identifications. I just put the square because we were using that, okay?
All right.
But let me draw the circle here. So you have the field circle. And the way to get the projective, the real projective plane to dimension, this is A. This is also A, but the identification is like this. Hence, this point that is more or less at the beginning of A corresponds to this one. This point, which is the end point, has to be the same as this one. The end point A in blue, end point A in red. This is close to the end point of A blue and close to the end point in A red. You are here. So these two pictures, this will give you the real projective plane, and also this one. This is what we have with the sphere, the northern hemisphere, and the equator. Only the points on the equator have to be identified, and the rule is the one shown there. The points in the interior, they are not identified with any other points, only the points on the boundary. Any more questions?
Nope. That's fine.
Okay, then, so al menos que el gallo tenga una pregunta, un comentario.
Los de mi casa no.
Eso ya sale de cada vez que hablas, canta el gallo.
Otra
Ahí
vez.
está.
Sí.
Okay, so see you on Thursday.
See you next week.
See you.
Nice weekend.